So this quiz is actually going to add to the hydrocarbon stuff we've already covered with the new stuff that we've just recently covered. And the hydrocarbons hopefully will act as a buffer to help you do well on this quiz. So the first question says, to what class of compounds does CH3COCH3 belong? Whenever you see class of compound, what we're looking for is this here. Is it a halide, an alcohol, an ether, or so on? So in order to figure that out, it's going to be easier if we expand the condensed structural formula into the structural formula so that we can see what this functional group is. And I see right away we have an oxygen here in the middle of the chain. So you may be thinking, well, I think that's probably an ether. So you'll start to draw it, and we have a carbon with 3 hydrogens, and then a carbon, and then the oxygen, and then the carbon with 3 hydrogens. But you should notice right away that that second carbon doesn't have enough bonds on it. And we can't change what the formula really is, so I can't add in those 2 hydrogens that it requires. So this can't be correct, so I'm going to try something else. We're going to do instead a double bonded oxygen like we see in the ketones, and this time that works. Now all the carbons have 4 bonds, and we have a ketone. So this is going to be a ketone, and the explanation that you use, because it does ask you to explain, can just be the drawing. Next question, to what homologous series? So when you see homologous series, they're looking for this. Is it an alkane, an alkene, or an alkyne? So we're going to look at the formula now. We have C5H8. This is the molecular formula. So we'll look at the general formulas and see which one that fits. Alternatively, you could try to draw that out and make it work. I think that might be the more difficult solution, but we're going to look at the general formula. So if it was an alkane, N would be 5. The subscript on H should be 2 times N, or 2 times 5, which is 10, plus the 2, which would be 12. So it's not an alkane. For an alkene, for the H's, you would have 2 times 5, or 10 hydrogens, and that doesn't work. If N is 5, we have 2 times N, which is 10, minus 2 is 8, and that does fit. So this is going to be an alkyne. And to justify that, I'm going to put the general formula for alkynes. All right, next we are going to be naming. So it's really helpful before you get too far in a name to highlight or box in or circle anything that is significant. So I see right away I have a nitrogen. I don't have any oxygens or anything else in there. So when I go to look in my table R for what this is, I'm looking for nitrogen. So you can either look in this column here or this column here in order to find the one with just nitrogen. And here it is. This is showing you that the nitrogen could have up to 3 different side chains on it. Okay, so this is our example. We've gone through how to expand those out, but this is essentially a 3-carbon chain attached to a nitrogen that has just 2 hydrogens on it. Ours is a little different. We have a 3-carbon chain attached to a nitrogen, but on the other side of the nitrogen we have another carbon. When you have an amine with multiple branches on it, you're going to name it like this one, in this case propanamine, and actually this will be propanamine. So you take your number of carbons. You would normally name a 3-carbon single bonded chain as propane, and you drop the E and add amine. But in this case, because we also have this little branch on there, we need to include that branch. So not only are we going to call this propanamine, and technically it is on the first carbon, that amine group is on the first carbon, but we also need to include this 1-carbon branch. And just like in the hydrocarbons, all we do is call that methyl, one carbon branch. So it's methyl 1-propanamine. All right, next one, I see a couple of significant things. I see a fluorine, and I also see a double bond. So in 2008, IUPAC actually changed the numbering preference for naming hydrocarbons, or even those that contain functional groups. And the preference goes to the double bond. So when we're numbering our carbons to start naming this, we have to start from the end of the chain that gives our double bond the lowest number. So when we go to name this, we have a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain. So that's oct, with one double bond, ene, that's on the third carbon. We can't now switch the end of the molecule that we count from, so our fluorine is actually on the 7th carbon, so it'll be 7-fluoro-3-octene. So the preference goes to the double or triple bond and then to the halide. All right, next one, this didn't copy real well in from my PDF, but that's an H there. But what's significant in this one is this group here. So we'll look in table R, see if we can find that. And as we go down the group, I see something like that here. These are just rotated, but remember, those are three-dimensional. They can rotate, and it's still the same thing. So this is an organic acid, and all we do is count up our number of carbons and add oic acid. So we have 2 carbons here, which would be ethane, but we'll drop the E and add oic acid. So that's ethanoic acid, which you guys have actually used in lab. It smells like vinegar. Next one we have here is a hydrocarbon. Again, it didn't pull in well from my PDF, but that's an H. My longest chain is 3 carbons long, so I would call that propane. 3 carbons single bonded, but I have 2 1-carbon branches. So this would be dimethyl. And then you don't have to in this case, but you probably always should give the addresses of each of those. So that is 2,2-dimethylpropane. Next one we're looking at was given to us in the condensed formula, so you are likely going to want to blow that up. First carbon has 3 hydrogens. Next one has just 1. Last one has 2. So right now, the way I've drawn this, there aren't enough bonds on my carbons, so it must be that we have a double or a triple bond between them, and making that a double actually satisfies my 4 bonds that I need. So this is a 3-carbon prop with a double bond, ene. And again, you actually don't need the number here, but I think you probably always should include it. And we would count from the right side, since that gives my double bond the lowest number. So that's 1-propene. The next one is also condensed, so we're going to blow that up a little bit. We have carbon with 3 hydrogens, then a carbon with a double bonded oxygen, and then a nitrogen with 2 more hydrogens on it. So this has not only a nitrogen, but also a carbon with a double bonded oxygen. So we're going to look through our list here, and we're going to find, there's a nitrogen, no double bonded, here it is, right here. And this shows that this carbon could actually have more carbons off to its left, and this nitrogen could actually have carbons off of it as well. This one, by the way, off of the nitrogens, we would just treat like they were branches, call them methyl or ethyl, however many carbons they have. The carbon chain that has the double bonded O is always the one that will get that amide ending. So it doesn't matter if the branch is longer than the side with the double bonded O. The side with the double bonded O always gets the amide ending. So this has 2 carbons, which we would call ethane, but we're going to drop the E and add amide. And it doesn't have any branches off the nitrogen, so we're done. Number 9, what I see as significant is an OH and another OH. So we're going to look for OH in our table R. And here it is right here. It's an alcohol, and we add OL and an address to it. So we have a 2-carbon chain, which would just be ethane. Now here's the weird part. There are 2 OH groups, so instead of just adding OL, we're going to add a DI before the OL. Just like when we had multiple double or triple bonds, you always put the DI right before what it is you have 2 of. In this case, we have 2 OH groups, or 2 alcohol groups, and we should give their addresses because they could both be on the same carbon, or in this case, they're on 2 different carbons, so it's 1,2-ethanediol. Last one on the front, the significant thing here is that O in the middle. So when I go to look at my list here in table R, I see that right here. It's an ether. And we just name our 2 chains, the shorter one, then the longer one, and then tag on ether. So that makes this the 2 carbons shorter, so that would be ethyl. And then the other side is 3 carbons, so that's propyl. And we just tag on ether. Now we've got to draw some of these, and this first one's probably the hardest one for students to do. We have propyl methanoate. And in order to figure that out, we should probably have our reference tables. So now we have our different reference tables, and in order to figure out even which class of compounds this belongs to, we can look at our examples, and you're going to see one like this right here. So that means this is an ester. Esters are tricky. They're tough to do. But if you've gotten this already written out in the expanded structural formula rather than this condensed one, you'll be able to see this better. But the methyl is this branch here, and the propanoate is this one here. And whichever one has the O on it, the O sticking off of it here, that's the side that's going to get the O8 part of the word. So the side with the O gets the O8. So when you go to draw this in the other direction, that's going to be important to realize. So when we look at this name, the part that has the O8 is the methane, or the 1 carbon, if you need a little reminder right here, the 1 carbon side. So I'm going to go ahead and start this with the 1 carbon side. And since that has the O8, it's going to get the O's. And then the propyl is going to be more like a branch on the other side. So that's 3 carbons. And then we need to make sure all the carbons have enough bonds, like so. And that is an ester. Those are tricky. Next one we have methyl ethyl propanamine. So again, looking at table R, we want to find one with amine in it. Here it is. And it's a nitrogen that could have up to 3 branches on it. And when you look back at that name, you'll see you have a 1 carbon, a 2 carbon, and a 3 carbon. So I'm going to put the nitrogen in the middle. And we're going to have a 1 carbon, and it actually doesn't matter which side you put these off of, a 2 carbon, and a 3 carbon. Now, if your nitrogen didn't actually have 3 chains off of it, it still has 3 bonds. So let's say, like the example we have here, you have just the 1 chain on it, propane, okay? So nitrogen needed 2 hydrogens to have all 3 bonds. So nitrogen always has 3. Oxygen, if you look back at this, always has 2 bonds on it. And carbon always has 4. All right, next one we have butanol. So we're going to look in table R to find something that ends like that. Oop, that's OL. Here's one that's AL. And what it is a chain of carbons, and it has a double bonded oxygen. And if you notice, this is an H here, meaning that there aren't any more carbons off to the other side. So that double bonded oxygen is on the end carbon or terminal carbon. Since this says but, that's 4 carbons. And on one of the ends, it doesn't matter which end, I'm going to pick this one just because there's more room, you're going to have a double bonded oxygen. Then that would just be another hydrogen, and then make sure all your carbons have enough bonds. Next one, we have 2,4-hexadiene. I'm going to, again, try to avoid these ones on your actual quiz, but it's not a bad idea to be practicing them. They theoretically could be on the exam at the end of the year, although I haven't seen it happen in a long time or ever. So we have a 6-carbon chain. 1, 2, 3, 4, 5, 6. And there are 2 double bonds. One is on the 2nd carbon. The other is on the 4th. All the other ones have single bonds. And then we're going to add in hydrogens until all of the carbons have a total of 4 bonds. Next we have 3-ethyl heptane, again just a hydrocarbon. This one is going to be hept long, or 7 carbons long, all single bonded. And on the 3rd carbon is a 2-carbon branch. I didn't leave myself a whole lot of room here. 3rd carbon, 2-carbon branch. And now we just make sure that every carbon has a total of 4 bonds by tacking on hydrogens, like so. Next one, we actually do have a functional group. We have a halide on a hydrocarbon chain. So we're going to have a chlorine tacked on to the 1st carbon of a 4-carbon chain. That's what bute's telling us. 1, 2, 3, 4. But it's also telling us we have a double bond on the 2nd carbon. So here's my 2nd carbon, double bond. Rest must be single. And off of my 1st carbon, I have a chlorine. All of the halogens make just 1 bond. You don't have to worry about putting other bonds on the chlorine. Next we have 2,2-propanediol. Di is just telling us that we have 2 of whatever that OL is telling us. So let's look through our list. The OL is right here. It means it's an alcohol and it has an OH group, or in this case, because of the di, we have 2 OH groups. So we're going to draw our 3-carbon chain, and they are single bonded. And off of the 2nd carbon, I have an OH group. Oxygen always has 2 bonds. That 2nd bond is with the hydrogen here. So I can't attach anything else on that side. So my other OH group that's on the 2nd carbon goes down here. And then make sure all your carbons have a total of 4 bonds. Next one we have ethyl propanamide. So we're going to look for what the amides are. I'm going to put this in the way for a second. So my amides are way down here, and the amides have a carbon with a double bonded oxygen that's attached to a nitrogen. So let me put that out of the way for a second. What's weird about this one is we have propanamide, but we also have an ethyl. And if you look back at that example at the bottom, and you look at this, this is that branch that you could have off the nitrogen. That's what that ethyl is. So we're going to go ahead and draw our propan, 1, 2, 3, with the double bonded oxygen, and then the nitrogen is also attached to that same carbon. And then off of that nitrogen is where we're going to put that ethyl, or 2-carbon chain. All of our carbons have a total of 4 bonds by tacking on hydrogens. And then don't forget, nitrogen always has 3, so this must have another hydrogen on it. Those ones are tricky. Next one, we have an ether. A reminder what ethers are. Here they are. They have an oxygen in the middle, and just the 2 chains. So we have an ethyl chain, which is 2 carbons, then the oxygen linking it to the 3-carbon chain. Off of each, you need a total of 4 bonds. Careful you don't put them on the oxygen, because oxygen just gets 2 and it's all set in an ether the way it is. Next one, we have butanone. So when we go ahead and look at table R, you're going to find the one is here. That makes it a ketone, which means we have a double bonded oxygen, but notice that it's in the middle of a chain. There's got to be carbons on either side. When it's at the very end of a chain, it's an aldehyde. So with a ketone, they tell us which carbon it's on. So we have 1, 2, 3, 4. That's what the but is telling us. The one is telling us it's a double bonded oxygen, and the 2 tells us which one. All your carbons need to have a total of 4 bonds. Be careful you do not put one on this carbon. Because of this double bond, it already has its 4. And that's it.